Okay. So, question 6. Figure 1 shows coils P and Q linked by an iron bar. Coil P is connected to the battery through a variable resistor with a switch S. Coil Q is connected to a center 0 ammeter. Initially, the variable resistor is set to its minimum resistance and S is open. Describe and explain what is observed on the ammeter when S is closed. Okay? Well, the first thing that will happen, that you will observe, so the ammeter will initially spike or be displaced. Be displaced before returning to 0. Okay? That's because as current goes from 0 to its value, it will induce a magnetic field which induces an EMF in Q. Once the current is constant, there is no change to induce the EMF. Okay, so basically, the second that you close this, you have a changing current. So that changing current changes the magnetic field in the iron bar. That, in turn, that changing magnetic field will induce an EMF in our coil. But as soon as the current is constant, there's no more change. There's no delta phi. So we're not going to have an induced EMF in the second coil once that happens. So the key thing is that initial reading goes back to 0 with the explanation. So describe and explain. So with S still closed, the resistance of the variable resistor is suddenly increased. Compare what is now observed with what was observed in part I. Explain why this differs. So, the ammeter will displace in the opposite direction Why is it doing that to me? Okay, so the ammeter will displace in the opposite direction before to 0. Okay. It is opposite because the current is decreasing instead of increasing. Okay, so again, you have a change in your current, at least temporarily, where the current is now decreasing instead of increasing. So because it's an opposite change, you will have an opposite effect. Okay? So that's what we are looking at. Yeah. Okay, next question. So figure 2 shows a 40-turn coil, cross-sectional area of 3.6 times 10 to the minus 3 meters squared, with its plane set at right angles excuse me, to a uniform magnetic field of flux density of 0.42 Tesla. Calculate the magnitude of the magnetic flux linkage for the coil. Select an appropriate unit for your answer. So we're at 90 degrees, so we don't have to worry about sine, cos, anything. So flux linkage N phi is equal to B A N. Okay, which is 0.42 Tesla times 3.6 times 10 to the minus 3 times 40, which equals 0.42 times 3.6 to the power of minus 3 times 40 which equals 6.0 times 10 to the minus 2. 6.0 times 10 to the minus 2. And the unit is the Weber turns. Okay, because the Weber is B times A. That's the magnetic flux. And then the linkage is times the turns. Because turns is not really a unit, just writing the Weber is also acceptable. Okay, so rotated through 90 degrees. So a 90 degree turn takes us from the min to a max. So it takes us from our maximum to our 0. So EMF is equal to N delta phi over delta T. N delta phi in this case is just going to be our flux linkage, okay? Because we are going from 0 flux linkage to this value, or from this value to 0 in our amount of time. So 6.0 times 10 to the minus 2 divided by 0.5. which equals 1.2 times 10 to the minus 1 volts. Okay, and I'll do our multiple choice ones here with the in this video as well. So question 7, transformer has 1,150 turns on the primary coil and 500 turns on the secondary coil. Primary coil draws a current of 0.26 amps from a 230 volt AC supply. The current on the secondary coil is 0.5 amps. What is the efficiency of the transformer? Okay, so why do I not have my formula sheet near me? Okay, so it's actually sort of a two-part thing. So our voltage, so we need our new voltage. So VP, actually I'm going to do it like this. Vs over Vp is Ns over Np, which means Vs is equal to Ns Vp divided by Np, which is 11, oops. Make sure to get it the right way around. 500 times 230 divided by 1150. That's not right. 500 times 230. Why did it divide? Times. Divided by 1150 is 100 volts. Step down transformer, so sanity check there. So I am lower, that's what I'm supposed to have. That was what gave me pause, is that my calculator spat out a number that was bigger. Okay, and efficiency is IS VS divided by IP VP. Okay, basically power output divided by power input. So 100 times 0.5 divided by 230 times 0.26 equals and I get 0.836, which is 84%. Okay, now a lamp rated at 12 volts at 60 watts is connected to the secondary coil of a step-down transformer. and is at full brightness. So it has that means that it has 12 volts going across it. Okay. The primary coil is connected to a supply of 230 volts. The transformer is 75% efficient. What is the current on the primary coil? So we just work backwards a little bit here. So IS is the current that's flowing through our bulb. So that's 60 divided by 12. Just rearranging P equals IV. So that's 5 amps. And in this case, 0.75 is equal to... Oh my god, why did I do that? Okay, didn't have to do that at all. Could have just used 60. So 60 watts out. Divided by IP times 230. So IP is equal to 60 divided by 5 times 230. Oh, 5. Can't even see properly here. .75. .35 amps. B. Let's check my mark scheme. Hooray, I did it right. So yeah. There we go. I think that's it. Yes, we are now at the mark scheme. Okay.